Clay's here.
Hi. Now we can go to the next discussion by Clay, and I hope people that had questions, they're still around, and they can start asking questions.
Okay, so maybe let's start. Actually, am I in the right place? No, let's go back to here. Let's start with any questions people had.
So there is one question already by Enrico.
Okay. Go ahead.
Go ahead, Enrico.
Oh, sorry. Hi, Clay. Question is, first of all, how do you find the higher form symmetries in a theory? And another question I have, I guess that everything that you said works both for Lagrangian and non-Lagrangian theories, but please correct me if I'm wrong. And the third question that is a little bit more esoteric, but is like in the master, you're taught that you can add like a total derivative to the Lagrangian without changing the theory essentially. What happens if you add the total derivative to the Lagrangian? Of course, the currents that you compute by Noether's theorem, they change. But if you integrate them over all space, since the fields go at zero, at infinity, the new terms that you're adding essentially do not contribute to the charge.
Yeah.
But here, my understanding is that you're computing this defect operator not over all the spatial slide. You're also, for example, taking spheres and such, right? So my question maybe to Naive is this defect operators that you're working with unique or not? Because by my naive understanding, if you add that total derivative, they change. Thank you.
Let me answer the third, the technical question first, which is about improvement terms. So yeah, the improvement terms don't matter for the reason that they don't matter in general, which is that I'm imagining this D-1 submanifold is closed. So it's something like a sphere. Think of it like something without a boundary. In that case, we won't, the integral of a total derivative will be 0.
I agree, okay.
The second question was about whether anything I'm saying has specifically to do with Lagrangian theories or not. The answer is no. I'm trying to, in fact, develop a point of view that works sort of intrinsically for any QFT. And the first question, I think, is the most interesting question, which is, how do you find the higher form symmetry of a quantum field theory? That is a tricky question. And you could ask another question, how do you find the ordinary symmetry of a quantum field theory? So one way, and in fact, kind of there's no sort of general recipe. You need to know something about your theory. But the way I'm building up in the talk is that, well, so for instance, I told you here that U1 free Maxwell theory has 2 U1 one-form symmetries. Now you say, well, that's very restricted. That's just about free Maxwell theory. Well, later we'll see what happens when we add charge matter. Then we'll see, okay, what happens, what is the one-form symmetry, say, of SUN gauge theory? And then we'll see what happens when we add charge matter. So we'll build up sort of a sequence of richer and richer examples till the point where we kind of have a lot at our fingertips. But if you ask, in a general strongly coupled non-Lagrangian theory, how do I find the symmetry? I think that question is just as difficult whether you're talking about ordinary symmetry or higher form symmetry. How do you know if some strongly coupled theory has Z2 ordinary global symmetry? That might not be so easy, right? Maybe there's a selection rule that you look at on the local operators. More intrinsically, you would just have to find this topological operator. So that requires you to know something.
Actually, this as a byproduct of my question, thank you for the answers, is how do you find exactly, for example, for non-Lagrangian theory, how do you find the Q, since you cannot use the Noether theorem to find Q, for example?
You mean if you're talking about a continuous symmetry when Q exists?
Yeah, for example, yeah.
Well, I mean, you need to start from somewhere. So I think that there are some lectures about, say, the conformal bootstrap happening. So for instance, if you're talking about a continuous global symmetry, you might hunt for the current. A current is a very special operator because it's an operator that obeys a differential equation. So that's one possibility. But you need to start with something. Okay.
Other questions? So there's a question from Lucas in the chat. So he's asking if it's possible to include non-local charges that appear in integrable theories.
Is it possible to include non-local charges that appear in integrable theories? That's a good question. That doesn't naturally fit into this framework. Yeah, so let me say that I don't know of an answer to that. But I don't know if it's impossible, but it's certainly not within the realm of things that I'll talk about.
I would probably come back to this example of Maxwell theory. So you defined the Q-form symmetry, right, in terms of existence of certain cycles, right? So in case of Maxwell, there should be 2 cycles, right? Or
yeah, I mean, I would say that once you have a line operator in your theory in 4 space-time dimensions, there's automatically a 2 cycle, which is the 2 cycle that surrounds the line operator. So no, I don't need to be in a fancy manifold to see that there are charged objects, right? This can all be done locally. Once you have a line, there's something that surrounds the line.
but then the statement is that you have as many currents, right, or as non-trivial cycles, right? 1 per cycle. So
you have different ways of measuring the charge, right? For each non-trivial cycle, you can get a different charge. That's right.
but here you seem to have like the same cycle, but 2 charges, electric and magnetic.
Well, that's right, because I have 2 currents. F and star F are different currents. This is a bit confusing because here, I told you that star J is closed automatically, but here I'm saying something else, right? I'm saying that star J is conserved. So that's why this leads to, F leads to 2 different currents, the electric and the magnetic, right? The equation of motion and the Bianchi identity are 2 different equations. Okay, if there are no more questions, I can talk more about Tuft lines, and I can also talk a little bit about another basic example, which is the example of axions, which is a good one to have in mind.
There are actually some questions.
Okay, yeah.
So first from Ahmed. Ahmed, please ask your question.
Hi. So gauge symmetries are not actually symmetries; they're redundancies. So my question is, can we have a gauged version of a higher form symmetry?
Yes, absolutely. And we will talk about that more. But the first sort of a precursor question to your excellent question is, what is a gauge field? Before, gauging the symmetry means is sort of summing over some kind of notion of gauge field, right? Like if you gauge an ordinary symmetry, you introduce an ordinary gauge field, and then you do a path integral over all the possible gauge field configurations, modulo this redundancy. And so the first thing we're going to need to know is what is the right notion of a gauge field? So we'll talk about this in detail, but just as a precursor, with a current, it's sort of easy. So if you have J with P indices, you want to include a term that's like like this, right? You want to modify the action by a term like this. So this would be a p-1 form current. Sorry, a current for a p-1 form symmetry. So if p is 1, this is a 0 form global symmetry, and then this is the gauge field. And so it's a p form. So for ordinary global symmetries, which corresponds to p equals 0, it's p equals 1 in this notation. It would be a 1 form. For a 1 form symmetry, it would be a 2 form gauge field. And then the gauge transformation rules are that B can change by B plus D of something of 1 index lower. And that the action, roughly speaking, should be preserved precisely because this shift should drop out due to the conservation equation on J.
Right. So we'd have a theory of higher extended objects, right?
Yes. So for an ordinary gauge field, one thinks that kind of the basic building blocks are things like line operators, Wilson lines. Here we'll have Wilson surfaces, Wilson objects of dimension p. Or you could integrate B over a p-dimensional thing.
Okay, thanks.
Yeah, so we'll talk about it more, but it's definitely the right line of thought.
So we're getting more questions. The next one is from Rohit.
Hi, this may also be something you'd probably plan on discussing, but so if you wanted to have these symmetries being broken spontaneously, they'd have to act on the vacuum state in some sense, right? So do these things also act on states, not just line operators?
Yes, I think I said something about that up here, which is what's going on in the Hilbert space. So imagine we have a situation. So most of the discussion was Euclidean, but let's go back to a situation where we have a Hilbert space. So space is y d-1, some d-1 manifold, and time is perpendicular. And so we have some states in this Hilbert space, and we would like to understand what is the implication? Are there global symmetry charges, or and so forth, and how do we see that? And what we find here is that a Q-form symmetry gives us, let's do the continuous case, which is what I've kind of written here. A continuous Q-form symmetry gives us one conserved charge for each non-trivial d-1 minus Q cycle in space, which is this y d-1. So, or again, orient yourself first by considering the case Q equals 0. So Q equals 0 is an ordinary symmetry. And then I'm saying that a continuous ordinary symmetry gives us one conserved charge for each non-trivial d-1 cycle in y d-1. Well, since the dimensions match, the only non-trivial cycle is y itself. So there's one charge. But if we're talking about, say, a one-form symmetry, then there can be more charges depending on the different cycles that we have inside Y. So it's those symmetries that one would talk about being spontaneously broken.
I see. So the point is that there's only one way of, okay, so there's exactly one action of these charges on states, and depending on which current you pick, you get different values or something.
Well, let me just do an example, so just to see if I can make it more clear. So let's do Q1. Okay, so we've got a two-form current. So d mu, j mu nu equals 0. So star j is d-2 form. How many charges are there? Well, let's, for instance, take y d minus 1 equals S1 times S1 d minus 1 times. So it's a big torus, d minus 1 torus. Well, the charges we can get by integrating star j over a subtorus, which is dimension d minus 2. Star j is a d minus 2 form, so it wants to be integrated over a d minus 2 submanifold inside here. This is a torus of dimension d minus 1, so there are lots of subtori that we could choose. So, for instance, I could integrate it over all the thetas, all the angles except for the last one. That would give me 1 charge. I could integrate it over all the angles except for the second to the last one. That gives me a different charge, etc. So so there are multiple charges.
Okay, so wait.
So when one discusses spontaneous symmetry breaking in infinite volume, we would be talking about charges like this in the limit where, say, the torus is becoming infinite volume.
So would that be a Hilbert space interpretation, or is it a different kind of spontaneous symmetry breaking?
No, I'm trying to say that it's the same. So this is the Hilbert space interpretation that I gave you up here. I've just done it for a particular case, q equals 1, right here.
Okay.
And what I'm telling you is that a one-form symmetry is giving us multiple different charges. And when we talk about spontaneous symmetry breaking of a one-form symmetry in infinite volume, we are talking about the breaking of these charges acting on the vacuum.
Okay.
Maybe just a comment in this direction also. Is there any well-known theory that could be an example to illustrate this question, this point, with tori, or let's say a symmetry that has more than one cycle?
A symmetry that has more, well, in quantum field theory, what the spatial manifold is my option. So I'm permitted to do quantum field theory on any choice of spatial slice. So, I can choose why. It's not a theory dependent question. So, we just went over the fact that Maxwell theory, U1 gauge theory, has 2 one-form global symmetries. So, I can study Maxwell theory on a 4 torus and the Hilbert space being a 3 torus, the spatial slice being a 3 torus and time being a line. And I could ask, how many charges are there in that Hilbert space? And I would get exactly this kind of situation where I'd be integrating F or star F over the various different toroidal cycles.
Okay, I think this answers. There was a question from raised hand from Shuhan Tiang. I don't know if he's here still.
Yes, I'm here. Thank you.
Okay.
Yes, so I have a maybe very naive question. So
Good.
So in this example you gave me here, you define 2 different U1 symmetries of the free Maxwell theory, right?
Yeah, right here.
Can they be defined classically, or so say are they symmetries of the classical Lagrangian, the classical Yang-Mills Lagrangian, or they only can be defined in the quantum field theory? That's
a very good question. That was sort of the next thing on my hit list when we got cut off on the lecture, but maybe I'll talk about it a bit right now. So new page. Good. So a what do I want to say exactly? So this one is a symmetry of the classical Lagrangian. By that, I mean, I could define a transformation on fields. So I'll briefly say it, and then maybe we'll talk about it. Well, no, let's just do it. Okay. So let's look at the transformation on fields. Okay, so we have U alpha, which is this. This is for the electric symmetry. So let's work locally. Which means that I'll take sigma to be the XY plane. At t equals z equals 0. So we're imagining we're basically in R4. Sigma is the XY plane, t and z are 0. That's and so this is our u. And what I'd like to show you is that we can think of this u as being related to doing a simple transformation on the fields. So let's set temporal gauge. So AT equals 0. And then we'll remember that AT is 0 star f sub xy. Remember, star f is a 2 form. That's what we're integrating, and we're integrating over the xy plane. So I'd like to know what its xy components are. And this is like dt a z. There would be a corresponding term zat, but I set it to 0 because of temporal gauge. Now, dt az is canonically conjugate. To az, right? This is the time derivative of az, so it's canonically conjugate to az. So therefore, I learn the following nice fact. U alpha ai U alpha inverse equals. Okay, so if I is not equal to z, nothing happens. If I equals z, then here I'm exponentiating the momentum conjugate to az, and I'm acting on az, so I should generate a shift. So I shift az by alpha delta of z delta of t. So here, A learned is that A has been shifted by a flat connection. At least it's flat away from U alpha. And indeed a symmetry of the Lagrangian. So you can check that this kind of shift is a symmetry of the Lagrangian. So and then by the Noether procedure, you would indeed compute the current and so forth. So that's for the electric one, it's sort of as expected. There's a kind of symmetry of the field variables in the Lagrangian. There's a corresponding Noether current, and one can proceed that way. For the magnetic one, it's not so simple. And that's kind of closely related to the fact that the charged magnetic objects are the 't Hooft lines, which are disorder operators. And disorder operators are not so easy to define in the classical theory. They make more sense in the quantum theory. So I don't know if this is kind of a long answer to your question, but hopefully it clarifies something.
Yeah, thank you. But okay, so maybe here things get easier because you are considering the theory on the three-dimensional Euclidean space, whose topology is kind of trivial. So if you replace the R3 with a more general manifold.
No, this was a local calculation, right? So I mean, so every 2-cycle locally looks like this, right? So in a small patch of the 2-cycle, you could approximate it by its tangent space. You could find the canonically conjugate variable. You can write this formula in general. I just didn't do it.
Okay.
Right. This would be like the delta function that's dual to this surface sigma in general. Something that when you like it's like a bump function with total integral 1 away from the surface. Sorry, over the surface when you integrate through the surface, right? Like this is delta of z, delta of t, because this thing is the plane t equals z equals 0.
Okay. Yeah. Thank you. So
that part, there's not there's not really any loss in generality in taking sigma to be the xy plane and working locally.
okay. And what can one say in general? So
Well, I mean, U alpha of sigma acts on the connection by shifting it by a flat connection, which is where the shift is supported just along sigma.
Oh. Okay. Thank you.
Okay, we don't have other questions so far.
Okay.
There are a few questions in Slack. I don't know.
Oh, okay. I haven't looked at that yet. Maybe you can. Maybe people are expecting me to write answers there, though.
Yeah, I think so. And the first one is about literature. So I guess unless you have.
Yeah, I'll write something. Yeah.
Okay, and we still have about 15 minutes.
Okay, so maybe I'll talk a little bit about.
Clay, Tushar just raised his hand, so.
Okay, go for it.
So I just had a basic question. So just in elementary quantum mechanics, we think of transformation on any operator by, let's say, charge as the commutator or anti-commutator of that charge with that state operator. So now here in this like pictorial way of writing things or showing things, what would that mean? Like it would just correspond to, let's say, the U alpha surrounding the line operator minus the line operator being outside that U alpha, right? So that is just like what you had written,
well,
e to the power.
Yeah, except for except for I did the exponentiated version. So this is the version giving me e to the alpha q, not q. So it's the version where you replace commutators by conjugation. But other than that, what you said is correct. Because U is a group element.
Yeah, so these are finite transformations.
Exactly, yes.
Okay, thank you.
Okay, one more raised hand. Shuhan, please.
Yes, I'm just very curious about this definition of higher form symmetry. So, do they form a group or other algebraic subject in mathematics? Or
yeah, that's a nice question. So the version that I'm telling you about, I mean, in my talk, maybe I mentioned that there are sort of a sequence of generalizations of the concept of symmetry.
Yes.
So the simplest generalization, which is what I'm telling you about here, they will form a group, and in fact, an abelian group. So let's maybe talk about that a little bit. So remember we had this, we said that the group was from the fusion. So this was our group law. Now, when Q equals 0, that's the ordinary symmetry situation. In that situation, it's totally possible for things to be non-abelian. And the way to think about it, let's imagine D is 3. We can easily visualize three dimensions. And then, here's G1. I'm abbreviating UG1 as just G1, and here's G2. And I've taken the liberty of deforming this M down a little bit. And no way to push them past each other. So this is not equal in general to this. They could be equal if the group is abelian, but it need not be. Now, so this is the ordinary symmetry case. So codimension 1, ordinary. Now let's imagine we're doing, say, a one-form symmetry in 3 space-time dimensions. So D is 3. So now we'll have something of codimension 2. So that's 9. So here's G1. And here's G2. And now just the topological property allows me to change their order. Right? Just lets me come out of the page and move the order. So there's no way to enforce an ordering on them when they're codimension 2. So so this means that the algebra is the group abelian. So that's sort of the simplest situation. So if you just talk about the most vanilla notion of higher symmetry, where the symmetries of different dimensions don't talk to each other, then the ordinary global symmetry can be non-abelian, and the higher global symmetry is in general abelian. Now, there are further generalizations where something like a non-abelian structure is there. It's not exactly a non-abelian group, it's what's known as a higher group. And then there's yet another generalization, which is something called capital symmetry. But hopefully this answers your question.
Do they have any mathematical interpretation or what?
Well, this is an abelian group. So abelian groups surely have a mathematical interpretation. A higher group is a known structure in mathematics also.
But I mean, for example, do they tell me anything about the geometry of the manifold? Or
well, I think that's not the right question. You could ask, does the fact that in quantum field theory, the geometry of space-time is my option, right? We had this point just a minute ago as well, right? When we're talking quantum field theory is not quantum gravity. Geometries are not summed over. I get to choose, I get to be the deity in this problem and say space-time is the 4 torus. And that's true for all and then that's true. And I study my theory on that in that setup. So, the metric is my option.
Right, but you said in the beginning you can also consider theoretical quantum field theory, right? So maybe. Okay.
Yes, the topological quantum field theory also is the same, right? So unless you're talking about quantum gravity, when you're just talking about then the space-time is your option. You get to choose what it is. I can choose the topology and the geometry. A topological quantum field theory has the special property that the geometry does not matter, only the topology matters.
Okay, thank you.
Okay, we have one more question from Wayne Zhao.
Hi, Clay. Can you hear me?
Yes, I hear you.
So I have a confusion about the Maxwell theory. So when you have the ordinary U1, well, the gauge U1, if we take a global U1 transformation, generally we think of that having like a symmetry, or at least something that could couple to a one form current, right? As an ordinary ordinary gauge field. So what is the relationship between that global part of the U1 and these higher U1 for electric and magnetic?
Nothing super easy. The global, you're talking about, what's the relationship between the global part of the gauge group and these higher form symmetries?
Yeah.
Nothing very easy as far as I know.
So they're just completely independent. Just there's three U1s are hanging around.
The global part of the gauge group is seems more elementary, but is in fact a much fancier notion, because it's something that only makes sense when you study your quantum field theory in, say, some non-compact space with some suitable choice of boundary conditions.
Okay.
Right, it's not something, even though it's a U1, there's not really any current for it. So it's a bit of a funny beast. Whereas these notions of symmetry, the kind of notion of symmetry that I'm talking about here, makes sense even if space-time is compact, when there would not be any choice, there would not be any of these sort of global parts of U1s to talk about, or global parts of gauge groups. It's a good question, but as far as I know, nobody has really succeeded in putting those global parts of gauged redundancies on the same footing as standard global symmetries.
Okay.
Okay, the next question is from Rohit.
Hi. So is there any notion by which you can stack line operators to get surface operators, like symmetry-wise?
Stack line operators to get surface operators. By stack, you mean form some kind of mesh or something like that? What do you mean by stack?
I'm sorry, I missed that sentence.
Oh, I just asked for clarification of what you mean by stack.
Basically arrange. You had the picture with the line operator circling another line operator somewhere above, I think.
Yeah, here, yeah.
So could you by any chance have lots of U alphas arranged in a line so that you can create a surface in some sense?
Yes, that is a notion that is very important, especially in 2+1 dimensional quantum field theory. I'm not prepared to talk about it in much detail, but if you're talking about the QFT, if you're talking about the QF possible topics in theory of extended operators, this sometimes is called condensation in the CMT literature, condensed matter literature, sometimes anion condensation. And one thing that is meant by that is that, so in a 3D theory, often a TQFT with lines, you could try to, so say you have some line L, you could try to form a surface operator. And you can ask, what is this surface operator? And maybe the surface operator can be represented as some kind of mesh of lines. So you have this line L in some kind of mesh in here. So these are all L. So this process of taking a line and using it to make a surface is called anion condensation. It's quite important in topological field theory in 3 dimensions.
But would you get a lower form symmetry out of this?
No. So actually, in general, you don't get a symmetry. You just get some surface operator. I mean, I should say this is some kind of deficit in our quantum field theory education system, which is that we don't talk enough about extended operators in quantum field theory. We talk all about local operators, and there's a good reason for that. Those are the basic building blocks of quantum field theory. But operators, lots of extended operators exist, and most of them are not symmetry operators. So, for instance, coming back to the Maxwell case, where we had two one-form symmetries, we said the charged objects are these lines, the Wilson lines and the 't Hooft lines. So, but those lines themselves are not symmetry operators. They are not topological. Those are just some bunch of lines that exist in the theory. So the discussion down here is actually analogous. So, given a line, you can make a surface sometimes this way, but neither this nor this need be topological. They need not be symmetries.
Wait, but given a one-form symmetry, it is, right?
If this is a one-form symmetry, then this need not, it depends on how general of a concept of symmetry you want to make, but this is, in definitions that I've been using, this is generally not a symmetry.
I see. May I ask what fails? Is it just that it needn't be invertible, or are there more symmetry?
Invertible. It's not invertible generally.
Okay.
I mean, in the context of topological field theory, everything is topological, so that's not really something to check. But what is something to check is the invertibility.
Okay. Could I ask a second question, or should I come back later?
I think it depends. I can't see the hands, so if there's if someone,
No, I think you can ask. I mean, we have still a couple of minutes and not many questions.
okay.
So, is it a rule that topological surface operators that are associated with symmetries can only be defined on orientable surfaces?
Only be defined on orientable surfaces. I would say. I understand why you're asking. I would say yes, except for Z if it's Z2.
Ah, right.
Okay.
Okay, thanks.
Yeah, I don't know. We have maybe 2-3 minutes.
2-3 minutes and no hands raised, right?
No hands raised.
Okay. Well, maybe I'll just leave you all with another kind of elementary example. Do I have a card cut off in 2 minutes?
No.
Okay. Which is the theory of axions. So this is another basic example to have in your back pocket of higher form symmetry. So what's an axion? Let's be in 4 space-time. So we have a periodic scalar field. Let's call it A. And to say that it's periodic means A is identified with A plus 2 pi f for some dimension 1 constant f. So this is an identification in field space. And okay, so the action is as usual. The action is d mu a squared. Okay, so what are the symmetries? Well, there's a shift symmetry. A can shift to A plus some little bit epsilon. This is to be distinguished from the identification. A and A plus 2 pi f are considered the same field configuration. Here I'm talking about moving A a little bit, less than its period. So this is an ordinary global symmetry. So let's give it a superscript 0. Ourselves that it's an ordinary symmetry. This is the shift. This would be broken by a potential. In general. Of course, if we talk about potentials for axions, the potential must respect this. A goes to A plus 2 pi f, because this is an identification in field space. But it need not respect this A goes to A plus epsilon. Now there's a second symmetry. There is also string symmetry, which is a 2-form. So this one I should also say, what is the current here? So J mu is mu A, and d mu J mu equals 0, precisely because d squared A equals 0, because the free equation of motion is satisfied. And this jives well with the fact that a potential would break this symmetry. Of course, if you add a potential, you'll change the equation of motion. This symmetry will in general be broken. Now, the other symmetry is a 2-form symmetry, U1, 2. I'll call it string. And this exists because d mu A epsilon nu rho sigma d nu equals 0. So this is our current, 3-form current. So this is a simple theory in 4 space-time dimensions that has a 2-form global symmetry, the periodic scalar. And what are the charged things? The charged things should be, it's a 2-form symmetry, so the charged things should be surface operators. So what are the surface operators? So you integrate, so let's say there's a, so they're coded, let's draw a picture. So here's the surface, let's call it sigma. And around that surface is a 1-cycle gamma. So I've drawn it's a surface operator in 4 dimensions, so it's similar to a point in a plane in R2. So so that's what I've drawn here. And the surface operator has the feature that if you integrate dA over 2 pi f, you get n, where n is the charge. So that's the charged object for this 2-form symmetry. So this is another good example I just wanted to show you to keep in mind. Just like the Maxwell theory has these 2 1-form symmetries, the axion theory has a 2-form symmetry. That's interesting to study. Okay, so maybe I'll stop with this.
Okay, yeah, so we ran out of time. Thank you very much, Clay. So we'll continue tomorrow and with the next lecture of Clay in the afternoon.
Okay, very good. Bye, everyone.
Bye, Clay.